Alright, we're back with the second video here. We're trying to make sort of old school games in Java, specifically Super Mario Kart. I promised today that we would get to see some 3D projection, and we will, but we have a lot to get through, so I'm going to go ahead and get started. First off, last time I made these variables private. That was stupid. They need to be public so they can be accessed outside of the class. I realized that after the video. Like I said, sometimes I try to think about three things at once. Second of all, you'll notice that I've added to the project this new class here. We're going to be talking about that in just a little bit. The reason why it's already added before I started the video is because it's already a completed class. There's a lot to it, and I want to go through every line and explain it. If I tried making the video first by sort of typing it all out while talking, but it ended up bloating the video length to like 50 minutes or something. It was much too long, so I decided that I'm just going to have it already typed out and then just sort of go through it line by line because it is a lot. Another thing we're going to do is start using these, right? So we're going to go over to the desktop launcher. We're going to mess with this configuration here a little bit. I like to set it to not resizable personally. That it doesn't really matter. You can have the window be resizable if you'd like. And then we're going to set the height to game screen type game height. And I know what you're thinking. This is going to be a really small window, right? Because we only set it to 256 by 224. Well, you would be right, but we're going to multiply these variables by something to make the window not so small. And now you're probably thinking, well, what's the point now? Why not just make these numbers bigger? And the reason is we want this to be kind of a low-res game, right? The Super Nintendo was pretty low-res. If we made these numbers bigger, we would be increasing the sort of visual fidelity of our game a little bit, and you'll see why later, because we're going to use these numbers as sort of like pixels on the screen. So we want our game window to be bigger, but we don't necessarily want our game to be higher resolution because we're trying to sort of recreate the Super Nintendo look. In any case, that's the reason for such small numbers here. So we also need a few more things in this class, and these things I will type out. So we need an orthographic camera. An orthographic camera is basically just a camera that doesn't do 3D projection. It's just a basic game camera through which you're going to be looking at your world. And I know what you're probably thinking, well, we can already look at our world, right? We can, but say an object was off screen and we wanted to move to look at that or something, well, you would need a camera to do it. Right now, we just have one static view of our world. So just instantiate it. And then set, yeah, I spelled that wrong. And then sort of, let's just do it with caps lock. Set the size of it, game width, game height. Let's see. Oh, whoops, I'm getting ahead of myself. That's the position that needs a third variable. It's actually just, okay, whoops, we don't need that. Dot set, oh wait, sorry, dot position, dot set. Now we're going to set the camera's position just to be the middle of our screen. So we're going to go ahead and take this, just copy paste it, and then set that third dimension variable. We're just setting it to 0 because we're not dealing with the third dimension with this game. This is a 2D game, even though it will look 3D. And then we're just going to set it to the center of the screen. And then we're going to update the camera. The great thing about using a framework like Libgdx is we don't need to know the underlying implementation of this camera. We can just use it, right? So we're going to go ahead and update the camera after setting its position. You're going to have to update every time something changes with the camera. And then we're going to go down here to the render loop. And we're also going to do some stuff with the camera here. First off, we have to tell the sprite batch here what to project to. It's going to be projecting to our camera. Once again, don't necessarily need to realize what camera.combine means, we can just use it. However, it has something to do with the underlying matrices in the camera. As you can see, sort of matrix, it says in documentation there, matrix 4, the combined projection and view matrix. Don't necessarily need to know why that's the case, it just is. We're going to make a quick handle input method, which we'll use a little bit later, probably in the next video. Private void handle input, and that'll be what we'll be using to put all of our input sort of like key press things in. And then after we handle our input, we're going to update the camera again. Like I said, the camera has to know that we just did something that it needs to be aware of. Then we need to begin drawing with the sprite batch. This is our render loop after all. And all drawing will go in between the sprite batch, as we'll see in a second. Cool, so this class is basically done for now. Let's go over to, okay, that's done too. We finished this last time. Okay, cool, so we can start working on this now. So go ahead and make a class called PixelMap or PixMap3D, or whatever you want to call it, if you can find a more appropriate name for it. And then I'm going to take you through this class line by line and explain what I did here. Like I said, I know it's not ideal, but I tried a video typing all of this out and it just took way too long, especially with minor mistakes and stuff on my part and having to go back and correct them and all that. It's really just better if I go through it line by line. So first off, we have our class. It's extending PixelMap. So if you've never sort of come into contact with pixel maps before, or bitmaps, which are basically the same, similar, it's basically a 2D array that in each position, or a 2D matrix, a two-dimensional sort of array there that holds information about the pixels of an image. So as you can see here, I have this this grass image, which I can provide this for people if they just want to use the same assets as me. But I have this grass image that I've set as a pixel map, as well as this class being a pixel map. So that pixel map holds all of the pixel information for this grass image in a 2D array so that we can sample from it, as you'll see in a minute. Then this class is going to represent a pixel map too that we're going to draw to. We're going to draw other pixel maps on this one. And then it's going to be, so once we've drawn our, like, for instance, our racetrack pixel map, our grass pixel map is the ground, everything onto this one larger pixel map that this class represents, then we're going to draw it to the screen. Now that's what this is for, this pixmap texture here. Basically, once we're done drawing to this pixel map, the batch is not actually going to draw the pixel map to the screen. I don't think the batch actually does that. It draws textures, but not pixel maps. So what's going to happen is you see we set this texture, we give it this, the pixel map itself, this class. We're getting the format, which I'll talk about formats in just a moment. Setting it to true. This variable, it's use mipmap. It's whether you want to use mipmaps or not, just set it to true. I haven't really found that messing with that too much is worthwhile. Any case, in our render loop here, we're going to draw the pixel map, this, to a texture, and then draw the texture. The batch is going to draw the texture to the screen at the origin. So I believe that everyone is probably familiar with coordinate systems. 0, 0 is just an X and Y position. So at the origin of the pixel map there. Now, for Libgdx, I know that most would have the origin here. A lot of times in games, the origin is up here. So just keep that in mind. That would be 0, 0. Now, in any case, what's going on, we'll talk about these in a second, but what's going on with the constructor here. So for a pixel map, you have a width and a height. In our case, and we can go do that now, and go ahead and make the instance of it. Go ahead and instantiate it. So in our case, the pixel map 3D obviously is going to have a width and a height that is equal to our screen, and this is what I was talking about. We want a low amount of pixels, low resolution. And then the format, well, I've never known that so I've tried like all of these different RGB formats, and to me, none of them make a huge difference. You can try a different one than me if you want. I'm just going to go with the 565 one. You can experiment with it, see if maybe to your eyes it makes a difference. To me, it didn't. So then we're going to go in here and we're going to call the pixmap.render. And if you haven't typed everything out yet, that's fine. Because this is all we're doing with this class, right? We're just going to go in between the batch. We're going to pass the batch in now that it's began rendering. We're going to render everything in the pixel map, and then we're going to end the sort of rendering for this loop. It's going to go right back around, right? Clear the screen, tell the batch what to project to, all that good stuff. Cool. So keep going through this. We just call the super class. You know, it's extending this super class, so we're calling these super classes constructor. Really easy. The filter, this is telling how to sort of basically how to place the pixels relative to each other. You can pick bilinear or nearest neighbor. If you want to know a little bit more about these, I just suggest you Google them. But in general, I don't think for this project, choosing either one's going to make a massive difference. So I would just go with nearest neighbor and move on. We already talked about the sort of pixmap text here. I don't know why I did this twice. That's actually pretty silly. But anyways, not that it would have really made a difference. The computer would have probably just been like, you know, what the hell is this guy doing setting it twice? Anyways, and this is our horizon variable. So you're probably wondering what that is. Well, if you take a quick look at okay. If you take a quick look at not shopping, come on. Okay, if you take a quick look at Super Mario Kart, you can see there's the horizon line, and that's basically what we're setting with this, the horizon line up there. So we're just going to set ours at 30 pixels down. So for this horizon line, we're telling it to be 30 pixels from the top of the screen. You can play with that number if you want. It's totally fine. Mario Kart uses like very little screen for the background, which we're not doing a background today. By the way, this is just going to be all black, whereas this will be rendered. But yeah, they use very little here. It looks like you can use a lot or little. You know, it just depends on what you want. Now the grass, we're just making that a pixel map. If you're wondering what this file handle thing is here, well, basically it's just a link to your file. For some reason, the pixel maps require this file handle class. Textures don't, as you can see, but that's totally fine. Not a big deal. If you have it in your assets folder and you set up your assets folder in the run configurations, like in the last video, you should be totally fine. This is an absolute path. You know, some people say you should never do that in libgdx. Use gdx dot, I believe it's files dot internal. Yeah, use that, because once you actually make your game into an executable, you'll have to use that. This is an absolute path, and you'll want to use the gdx.files.internal if you ever plan on, you know, making the game into a runnable executable that you could like email it to your friends or publish or whatever. But that's just a small note. Now, what is this position? Well, that's going to be our theoretical position in the world. One thing to keep in mind is the reason why I say a theoretical position is because we're not making a 3D game, right? We have a theoretical 3D position because we're making a pseudo 3D game. You know, Mario has a theoretical 3D position. He also has a position on the screen. So this is the screen's coordinate plane, but there's also this three-dimensional coordinate plane. You have like a z-axis and your y-axis and sort of the x-axis there that he's in also. This is our theoretical three-dimensional position. And these numbers for right now are totally arbitrary. This third number represents your height above the track, which you can call y, z. You know, they've called it z here. That's totally fine. But just remember, this is sort of like your height above the ground. I said track. We'll have a track in soon, not today, but soon. In any case, this is your height above the ground. You can play with this number. It's not important until we really get moving around in the world, but that's just what it is. And these numbers, like I said, are pretty arbitrary for the moment. Now, what is this scale? Well, the scale is telling things how big they need to be relative to each other. And I'll tell you a little bit more about that in a minute. And what's the angle? Well, that's our angle. So when you have a 3D position, you are facing in a direction and therefore you have an angle as well as a position. This is your sort of like two-dimensional coordinates, or your, I guess, your full three-dimensional coordinates. And then this is the angle you're facing, right? If I'm standing in a field, I'm facing in a particular direction. So I have an angle relative to the world's origin, relative to 0, 0, right? Relative to position 0, 0, 0. And that's what this is telling us, our angle relative to that. You could set this to theoretically really any number. You could set it to 3.22 if you wanted for now. I just set it to 2 because it's a really simple number. This is also in radians, by the way, and not degrees. So this is not saying an angle of 2 degrees. This is saying an angle of 2 radians. If you want to know how to convert between radians and degrees, you can easily do that. I think it's just, there's a really small formula for it that has to do with like 180 time like over pi or something, and I think converts to radians from degrees or degrees from radians. It's a really quick Google search, but just know that this is in radians and not degrees. So don't put like 120 in there and expect it to be 120 degrees, right? Though you could put 120 in there if you wanted. It would just be a really big degree number. Cool. Anyways, once again, here we're just drawing to the texture, then drawing to the screen. I hope that makes sense using the batch that we passed from our game screen right here. I hope I'm not moving too fast. I think I'm going at a pretty good pace, but I also probably need to because we still have a lot of code left. Once again, if you ever have any questions or something, you can ask me in the comments. I'll try to answer them. Or you can attempt a Google search, which is sometimes helpful too. And in fact, I will link a really sort of useful article probably under this video that you can go to, and it's one of the places that I first learned how to do like mode 7 3D sort of projection and stuff like that, and a lot of this code is based off of that article, so it would be a good thing to go read if you want to know a little bit more. Now, anyways, so what's going on here? So based on our angle in the world, we're getting our direction. We're getting okay, so actually we're not getting exactly our direction, but it's not like this is telling us, forward, backward, whatever. But what we're actually getting here is a vector, a unit vector, which all unit vector means, I assume everyone knows, okay, so let me actually back up a little bit. A vector is essentially a point, right? So you can have like a 2D point, which would be like 900 by 700 or something like that, in a 2D plane. That represents a position, but a vector represents a position and direction. So this is going to give us information not only on our x coordinate position on the plane, but the direction we are facing also. And this is the same thing except for the y coordinate. So we now have a vector that is our x and y position that also represents our direction. That's why I called this dx and dy. Now, so and unit vectors are normalized, which just means that they're made to be less than or equal to 1, basically. And they're really useful because sometimes you get working with these big numbers or whatever, it gets kind of annoying, but a unit vector will do basically the same thing for you in terms of telling you your direction without needing those big numbers and stuff based on your angle. We're just using cosine and sine there. It's a little bit of basic trigonometry. I don't think that should be too confusing. It's not really a big deal anyways. If you don't fully understand what's going on here with the cosine and sine, you don't necessarily need to. You can always, I would hate to try to be a math teacher here, but in any case, the really important part is that you have direction x, your direction y, and we're going to combine this with position as you see down here. So what's going on here? Well, we have a double for loop because we're going to loop through the entire screen, in this entire pixel map, which now represents the screen, right? Because we've made it the exact same size as the screen. So we're going to go through it and we're going to decide what should be where, and then we're going to draw it to the screen. It's going to cover the whole screen, though in this case, it's not going to cover anything above the horizon. So as you can see here, we could start this at 0 and then we would draw the entire screen with no sky or background whatsoever, but we're going to start at the horizon, which makes sense, right? And then we're going to start at our position here at the horizon, and then we're going to go all the way across, fill in all those pixels, get to the next position, all those pixels until we've gone down the full height, which is 224 times. And this is going to go across 256 times for each of those, because that's our sort of game width. So we're getting the we're getting the y, and then we're going all the way across and filling in, getting the next y, going all the way across and filling in. And that's what this double for loop is doing. It's just looping through the pixel map that is our screen, starting at the horizon. That's why it's get height here and get width here, because we only want to go down as far until we reach the maximum sort of height of the screen. And like I said, once again, the actually I'll just sort of run it here. I'll just go ahead and show you. I was going to save it for the end, but it's fine. So you can see we have some 3D projection going on here. The grass sort of tiles are bigger up here, and they get smaller and smaller and smaller all the way towards the horizon. And this effect will be much, much more dramatic once we draw a screen into or a racetrack into this, as you'll see. But anyways, we're going to start up here. We're going to go across, decide what each pixel needs to be, whatever. Anyways, cool. So let's get going. What do we need first? Well, you get this distance and world space variable. What is this? Well, based on our position in the sky, multiplied by what we know we want our scale in the y direction to be, we need to divide that by essentially how far away we are from our horizon. And if at first we're going to be exactly our horizon, right? So this can be a divide by 0, but casted to a double, it's actually going to give us back infinity, because at the horizon, I actually should just keep this up. At the horizon, we're infinitely far away, or we should be anyways. Cool. And obviously your position in the Z is going to affect it, because the higher you are up in the air, the further you can see, right? If you're in a plane, you can see like the curve of the earth, but if you're laying on the ground, you can barely, your horizon is like maybe, a few foot ahead or something. But in any case, that's why this affects that. And like I said, once again, I'll show you what not having scale does in a moment, but it's just sort of there to tell everything how they should be relative to each other. Now what's going on here? This one I think is maybe the most confusing variable, but what this is actually getting is based on your direction sort of multiplied by your distance to the horizon currently, and sort of adjusted for scale. You're sort of deciding what the space here is. So at first, this is going to be sort of really large. Each pixel, each time you go over, is going to represent like a large distance. And that's going to tell us a little bit about how we have to sample our texture, right? So, or maybe not, but anyways, the point is what this is representing, this change, this delta x, this change in x and this change in y, is basically as you go across, how far across you have to go. I'll explain this a little bit more here in a second, because it's going to become relevant down here. Now what this is is where you are in the actual world, as opposed to the screen. This is where you need to sample based on sort of how far you are away, the change based on your distance, sort of the distance between pixels, the width and height of the screen, and also your position and your direction. We need to know where to sample the texture. So for example, it knows here to make the grass a little bit wider, but up here to make it smaller, right? And this will become more and more apparent as we start moving through this world with a little bit of input handling. Now, this is where things will start making a little bit more spins. So now that we have everything we need to know to go across the screen and fill in, we know where we're sampling the texture from. We know the distance sort of between pixels or whatever. We know our position in the world and on the screen. So what we're going to do here is we're just going to sample the texture, and sort of we're going to sample it so if we were to draw, you're probably wondering, why is this math.absolute value here in modulus operator? Okay, like, why can't we just sample straight from space x and space y? You could, but what would happen if you had if you just had nothing here but space x, for example? Like, if you have to cast it to an int, by the way, but like if you were to just have space x here, you could do this. What is it not like? Oh, it's the extra parentheses. Anyways, my parentheses are all messed up, but the point is that you could do this here and then just put space y here, but what it would do is it would only draw the grass tile once. You would have, which is what we're going to do with our track, right? We're only going to draw our track once. We're not having 52 tracks on the screen at the same time. But our grass, we need an infinite amount of grass on screen because that represents our base ground. So this absolute value and modulus operator allow us to infinitely loop through our texture every single frame so that no matter where we're looking, the grass always completely fills the ground instead of just having one 32 by 32 grass tile in the world and everything else is black, because it's just being cleared every time because it only draws it once. And then this is just the draw pixel function that pixel maps have. So now that we know sort of now that we know the pixel we need, this set color will set your pixel to be drawn. And then now that we know the screen position to draw it on, go ahead and draw it to the screen position. So we've sampled from our texture, we've set that as our pixel, and then go ahead and draw it to the screen. Once again, you have to make this differentiation between the screen and the world. The pixel map's drawing to the screen, but we have to sample in such a way that takes into account our world. Now here we go with this change again. So once again, and then once we've drawn this pixel, we have to add distance. So the screens, well, here's what's happening. So the screen knows automatically from the loop to move over one position, but this doesn't, right? This needs to, like, if we didn't do this, it would take the same pixel it sampled here and it would just keep drawing that. So it would look like this. It would look silly, right? So we have to sample the next portion of the grass. And in some cases, it might just be more green for a long time, but in other cases, obviously needs to know to sample to create that perspective look based on the numbers. So that's basically how this works. That explanation might have been slightly convoluted, and I'm sorry if it was. This stuff is a little bit, hard to teach, I've found. However, like I said, I will link that other article that I think explains it a little bit better than I do. And I also think that this will be a good starting point for y'all. We're coming up on 30 minutes here. That's not too bad, actually. But if you put this in, it should give you something like this. You can maybe experiment with different grass tiles, have something different. You can also experiment with different, we can do a couple funny things here. We can experiment with sort of different values. Let's try like 36 for that. Yeah, now it looks like we're much higher in the world. And then once we get some input handling in here in the next video, we're gonna be really rolling. Now you can see I already have this track in here, but it would sort of be, I don't think we have enough time to put it in today because I'm going to try to cap this at 30 minutes. Anyways, I hope y'all got something out of this video. Next time, I promise not only will we put the track in, but we will also put some movement controls in. And then at that point, we will be well on our way to sort of recreating the whole Mario Kart look, right? If you wanted to even sort of make it look exactly like this, you could probably get the assets somewhere. But anyways, that's it for this video. See you next time.